Welcome you all for another session on bending moment and shear force diagrams. We all know what it means by shear force. It is basically a force at the section of a beam which is developed by the material at that section to keep the portion of the beam in equilibrium state. And similarly, bending moment is also the moment generated by the material. All that we have discussed already, and we are drawing the bending moment and shear force diagrams for various cantilevers in the last few hours. And say one more such problem, and part of it is the same thing what has appeared in the examination. Okay, so it is a cantilever, and cantilever subjected to three types of loads. One is uniformly distributed load of 20 kilonewton per meter over a length of 2 meters. Then we have one point load 30 kilonewton, and that is at a distance of 2 meters from the fixed end. And at the same time, at the same position, I also have a moment which is equal to 100 kilonewton meter. So probably in our previous classes, we have taken only one load at a time. So only point load, so only moment, only uniformly distributed load, that kind. Now I have mixed all that, and then that is normally the case what we come across in the examination or in practice. Okay, so as usual, what is our reference? The reference for cantilever, what is that? It's always the free end. So the point D. So here in this case, D is the free end. We shall choose that. Now identify the portions. Which are the portions we need to analyze? Portions. What are the portions? One is DC, the portion DC. Then the other one is the portion CD. Because between D and C we have a load, and therefore between C and B I don't have any load. Okay, so C and B, that is another portion. And then B to A is the third portion. These are the three portions I need to consider for my analysis. Okay, so I shall start with what? Start with DC. Portion DC. So once you identify the portion, what is to be done next? Identify or take a section between D and C. So whatever the 2 points, 2 ends of the portion you have written here, no, D and C. Take a section between D and C. Draw the free body diagram. Okay, so I shall take a section somewhere here and draw the portion. Looks like this. This is my D, the free end, and this is where I have what is called as uniformly distributed load, and this distance is X, and this is where the section is. So this is X, and immediately I shall write down what is the range of X. For this portion, whatever I am analyzing, the range of X is, what is the smallest value? It is 0, the free end, and the largest value is 2 meters. That is at point C. If you go to X equal to 2, you are at C. X is 0, you are at D. So X value is between 0 and 2 meters. Then come back here, complete the free body diagram. Okay, what else is to be shown? I have shown the external load, which is a UDL 20 kilonewton per meter. Then at this section, this is the section. So this is where I have material, and this material is developing a shear force in the same plane, parallel to the plane, and this I would like to take it positive. So I know that shear force upwards is positive, and I have a bending moment, and this is my positive bending moment. This is Mx, and this is what is Vx. Okay, so don't worry about the sign convention. You can have your own sign convention. No problem. I'm worried about I want the numerical value, magnitude of the shear force, etc. Whether shear force upwards or shear force downwards is not going to matter. It will induce the same amount of stress. Okay. So therefore, whether you are taking upwards or downwards, it doesn't matter. The magnitude of the force is important for me, and therefore the sign convention you need not bother very much. So now everything is complete. Now what is to be done? Apply equilibrium conditions and express. Find out the expressions for those things. Let me start with Vx. I have written Vx with plus sign with an assumption that unknowingly I have already made sign convention. This upward shear force is positive. So any force in the downward direction is negative. So I have a uniformly distributed load, and the meaning of this is this load is acting in the downward direction. That means the force is downwards. How much is the force? So the length, so whatever is the magnitude, 20 kilonewton per meter multiplied by, what is the distance? How long? This is x meters. So meter cancels, you will have. Okay, this sum of this is equal to 0. I don't have any other force. Therefore, 3x is equal to 20 times x. So many kilonewtons. So the shear force, what is the observation? Okay, the shear force is not constant between D and C. Okay, so it is varying. Okay, that is, these are the observations. I want you to write it here. I am leaving it to you. What is the first thing? Shear force is not constant between D and C. Shear force is varying between D and C. The variation is straight line variation, or what is called as linear variation. I want you to write these three observations. Maybe after some time you will make these observations mentally and you can skip writing it. So initially practice that. So let me go back and complete the shear force diagram. It is 20 into x. So therefore it is a straight line. So we add D. So for that x is 0, therefore it is 0. And we add C. For that x is 2 meters, 20 into 2, that is 40 kilonewton plus. Okay, completed. So the shear force here is 0. The shear force here is 40 kilonewton. This is 40 kilonewton. And how is it varying? It is varying straight line. So this is the shear force diagram. Okay, let me complete now. Go for the bending moment. Start with mx. Unknowingly I have made a sign convention. What is that? The clockwise moment is positive. I am taking moment about this section due to all the forces. Vx is there only, therefore it will not have any moment. Then now I have a moment. Okay, for bending moment, whenever you have UDL, please draw one more diagram here. No problem. You can spend little more time and you can't afford to make very silly mistakes. You have x and this is where you are taking section. Okay, I am interested in only UDL. That UDL is going to be replaced by point load. Okay, so point load will be acting at the midpoint. This distance is x by 2. So how much is this load? This is equal to 20 multiplied by x. Okay, 20x multiplied by x by 2. That is the moment in the clockwise direction. Therefore, the moment is plus. Because mx clockwise positive. This downward 20x about this also is clockwise. Therefore plus, what is that? 20 into x, this is the force, multiplied by what is the distance? X by 2. Okay, any other force? No other force. This is equal to 0. So therefore 2 1s are 2 10s are. And mx is equal to minus 10 into x square. Mx is equal to minus 10x square. First observation, bending moment is not constant between D and C. Bending moment is varying between D and C. Okay, that is the second observation. What is the third observation? It is not straight line, it is a curve. The bending moment is a curve. So the moment you conclude that it is a curve, then get the bending moment at least at 3 points. At least at 3 points. Bending moment at D, then bending moment at C, and bending moment at x is equal to maybe between D and C, that is x equal to 1 meter. Okay, you are finding out the bending moment at 3 points. So bending moment at D, x is equal to 0. That is 0. That is minus 10x square, x is 0. And for the second one, bending moment at C, this is minus 10 into 2 square. This is equal to minus 40 kilonewton meter. And for this minus 10 into 1 square, this is equal to minus 10 kilonewton meter. Then come back here and write bending moment here is 0. And bending moment here is minus 40. This is 40 kilonewton meter. And in between the midpoint here. And how much is that? It is 10 only. And that means it is 1/4 of this. So something like this. This is 10. 10 kilonewton meter. So that means the curve is like this. This is the bending moment diagram. Okay. So this is the bending moment diagram for the portion between D and C. I hope so clear. Okay. Now let me go for the next one. What is that portion? What is the next portion? It is between C and B. It is between C and B. That is the next portion. Okay. So identify the portion. Draw portion C and B. Okay, what is to be done? Imagine a section between C and B. Between C and B. This is your C, this is your B. Somewhere here, take it, and this is how it looks like. So this is, and make this is your C. And this is not B. Please remember, this is where you have taken section. B is beyond that. Okay. So now this distance is, what is x? And immediately write down what is the range of x. What is the smallest value? Okay. It has to be between. It has to remain between C and B. Please remember, x is from here. What is the smallest value? It is 2 meters. And what is the largest value? It is 3 meters. From this end, if it is 2 meters, you are here. If x is 3 meters, you are here. So that if x is between 2 and 3, your portion C and B is covered. Okay. So now you have what is called as UDL. This is 20 kilonewton per meter. Any other force? No other force. Okay. So then you have what is called as a shear force, positive upwards, and this is my bending moment, the mx. Okay. Any other force? Nothing else. Go for it. Okay. So Vx start. Vx upwards. Okay. Then this is downwards. Please, one more thing I should do. We shall write down here. I know that this is 2 meters. And how much is this distance? This is x minus 2 meters. Right? So Vx upwards. Okay. Then this force, this is downwards, therefore it is minus how much? 20 kilonewton per meter, which is spread over 2 meters. It is not x meters, it is spread over 2 meters. 20 into 2. This is equal to 0. Therefore, Vx is equal to 40 kilonewton. So what are the observations? The shear force between the portion C and B is constant. It is not varying. Therefore, it is constant. Right? Okay. So, what is the shear force at point C? Point C, x is equal to 2. There is no x term at all. Therefore, it is 40 only. Throughout the length, it is 40. So, here this portion also is 40. 40 kilonewton. Then, therefore, in between it is constant. So, this is the shear force diagram for the portions C and B. I hope it's clear. Okay, then let me go for what is called as the bending moment. Okay, let me go for the bending moment. So whenever you are dealing with bending moment, and if you have UDL, you have to be little be careful. You have to get the equivalent point load for UDL. Okay, you have to get that. Okay, now for this only. So I shall draw one more. I don't want to have what is called as UDL. Say this is D and say this is C, and this is where I am taking section. This is where. Okay, so I have between C and D I have UDL. I want to replace that UDL by point load. So how much is the point load? So that is equal to 20 into 2, that is 40 kilonewton. So I know that this distance is 1 meter, and how much is this? This also is 1 meter, and how much is this? This is x minus 2 meters. Okay, now let me start. I am taking moment, okay, about the same section that I started kx. My clockwise moment is positive. Vx will not produce any moment. Then the moment because of this UDL that I have shown here. So what is the direction first of all? It is the same clockwise, therefore it is plus. Then how much is the force? Force is 40 km. And what is the distance? The distance between this point and this point. How much is that? So I know from here to here is x. Here to here is x, and this is 1 meter, and therefore this to this is nothing but x minus 1, or in other words x minus 2 plus 1, the same thing. This is equal to 0. Therefore mx is equal to minus, first of all, 40 into x minus 1, and it's 40 into x minus 1. What is your first observation? The bending moment is not constant between C and D because I have x here. Bending moment is not constant. Okay, what is the next? Bending moment is varying. Okay, what is the variation? Variation is a straight line variation because x raised to 1. Okay, it is a straight line. If it is a straight line, then bending moment you need to know at 2 points, join them, you will get the variation. What are the 2 points? Bending moment at C and bending moment at B. So to get bending moment at C, substitute the lower limit. X equal to 2. So x equal to 2. 2 minus 1. 1. 1 into minus 40. This is minus 40 kilonewton meter. And for B, substitute x equal to 3. So 3 minus 1, that is 2. 2 into 40, 80. This is minus 80 kilonewton meter. So complete the drawing. So I know that it is 40. Okay. The bending moment at C is 40 minus 40. Okay, fine. It is drawn. Then what is at B? At B, how much? It is 80 kilonewton meter. So how is it varying in between? It is a straight line. Join the 2 points by means of straight line. It is not a curve, it is a straight line. So okay, this is what is the bending moment diagram for the portion CD. Now you are left with the last portion. What is that? The portion is BA. Between B and A. Okay, portion BA. Okay, I shall write down what is the range of x here inside bracket. Okay, between B and A you take a moment. You take a moment. You have plenty of loads. This is your B and B. And somewhere here you have C. And somewhere here you have B. And this is where you have section. This is a section. This is at a distance of x. This is x. So I know that this is 1 meter, and I know that this is 2 meters. How much is this portion? From here to here is x. This is 3 meters. This is x minus 3 meters. Okay. Now at B, what do we have? I have a point load. How much? This is 30 kilonewton. Then at B, I have one more load, that is moment, which is 100 kilonewton meter at B itself. Then I also have what is called as the UDL, which is equal to 20 kilonewton per meter. Okay, so now let me start. Okay, let me before I proceed, I shall show what are called as the shear force, say Vx, and a bending moment, say Mx, Vx and Mx. All very mechanical, same procedure. But you have to have a lot of patience. You can't afford to make mistake because usually it is a wonderful question. If you are through complete this, you get full marks, and half of the marks what you require for passing, you get it. So therefore, very important, very crucial. So let me start with Vx. You have to exhibit a lot of patience. Vx, okay, Vx, this is one force, I have written it unknowingly, I have made decision. The upward force is positive, this is moment. Okay, this 100 kilonewton meter is also moment, skip it. Then 30 kilonewton, it is a force, it is in the downward direction, minus 30. Okay, proceed further. Then you have a UDM, I know that it is acting downwards, therefore it is minus. How much is the total load? It is equal to 20 into 2 meters. So this is equal to 0. Therefore Vx is equal to 30 plus 40. This is equal to 70 kilonewton. Observation. Shear force does not vary between B and A. Shear force is constant of 70 kilonewton throughout the length between the portion B and A. Go ahead. Okay, right. So shear force at B, it is independent of X, 70 kilonewton. So start here, say this is already 40 and maybe another 30. Drop, this is 70 kilonewton. And how about here? Here also is 70. This also is 70. And how does it mean? It is constant. So this diagram is what is called as SCFD, shear force diagram. I hope it's clear. Now let me go for the bending moment portion. Bending moment, let me write down. Okay, start with Mx. Okay, so since I have UDL here, okay, I shall draw what's called as D, and say this is C, and say this is B, and this is my X. So whenever you are dealing with UDL, okay, if you have to write down the Mx expression, before you do that, you replace UDL by point. Okay, so you have what's called as 20 into 2, that is 40 kilonewton. That is at the distance of, this is 1 meter. This also is 1 meter. And this also is 1 meter. And therefore this distance is what is called as x minus 3 meters. Okay, then this UDL. Then you have what is called as moment. This is 100 kilonewton meter, and this is anti-clockwise. Then you have what is called as point load 30 kilonewton. You have so many terms, and this is where you are taking moment. Okay, let me start. Come back here. To Mx. This is the moment. Unknowingly, I have written it as positive. Means the anti-clockwise moment is positive. That is the sign convention. Okay, this is force at the same section. Do not have any moment. Then let me take this 30 kilonewton. 30 kilonewton moment due to this about this section is also clockwise, and therefore it is plus. Therefore, the sign 30 value, 30 multiplied by what is the distance? This distance, x minus 3. 30 into x minus 3. Then I also have moment here. Please remember, it is not force, it is moment. And what is the direction of that moment? It is anti-clockwise. So anti-clockwise moment is minus for this case. Okay, so how much? It is 100 kilonewton meter. It is already, don't multiply it by x minus 3. It is already a moment. 100 kilonewton meter. Okay, proceed further. Then you have a UDL, that is what we have placed here. This plus or minus. the moment the force is downwards, this is the section where you are taking moment. The moment due to this is also clockwise, and therefore it is plus. This is 40 multiplied by what is the distance from here to here. So I know from here to here is x. This distance is 1. This 40 into x minus 1. This is equal to 0. Now all the moments, the sum of the moments must be equal to 0. This is what mx. If you go back and write down, okay, this minus 30 into x minus 3. This is plus 100. This is minus 40 into x minus 1. So this is, you can simplify or you can keep it as it is, absolutely no problem. You can keep it as it is and you don't have to simplify. Okay, just go through and make observation. The bending moment between B and A, what do you say? Because of the presence of x, okay, it is varying. Bending moment is varying. Bending moment is not constant. Okay, so if it are varying, then you have to make the variation. Is it straight line or is it curve? Okay, so here x raised to 1, here also x raised to 1. I don't have the product of x into x. Okay, such terms are not there. It is only x raised to 1, x raised to 1, and therefore the variation is straight line. The bending moment variation between B and A is a straight line. So once you make that observation, please make that is very important. Bending moment between B and A varies according to a straight line or linear variation. Okay, so for linear variation, so 2 points are sufficient. Which are those 2 points? One is at B and the other one is at A. Bending moment at A. For B, what is the value of x? So one more thing I forgot to write. Okay, so let me complete this. What is the range of x? X smallest value is 3 meters. And what is the largest value? It is 5 meters. Between 3 and 5. For B, x is 3 meters. X is 3 meters. 3 minus 3. If this becomes 0. Then this is 100 plus 100. So 3 minus 1. 3 minus 1 is 2. 2 into minus 40 is 80. This is equal to 20 kilonewton meter. Right? Okay, 3. X is 3. 3 minus 3 is 0. This is 100 as it is. 3 minus 1 is 2. 2 into minus 40 is 80. Therefore, this is 20 kilonewton meter. And what is the bending moment at A? Bending moment at A. For that, x is 5. So, minus 30 into 5 minus 3. This is 2. Then plus 100. Then minus 40 into 5 minus 1. Simplify this. This is minus 60. This is plus 100. 5 minus 1 is 4. 4 into minus 40. Minus 160. Minus 160 minus 60. Minus 220. Minus 220 plus 100 is minus 120 kilonewton meter. Okay, draw it. It is a straight line variation. What is the bending moment at B? The bending moment at B. Now I am talking about this portion. Don't worry about this value. So at this portion, for this portion, what is the bending moment at B? It is plus 20. Plus 20. So this is 80. 1/4 of that nearly. No need to draw it to scale, but you write a value. This is 20 kilonewton meter. Okay. What is the bending moment at point A? It is again negative. It is minus 120. It is more than 80. I'm sorry, I don't have a place here. Okay, I shall go beyond this 80 and draw it here and write it as 120. Okay, how does it vary? It varies straight line. Okay, there's something this way. So this is the bending moment. Okay, observe this point. Very, very important. This section. This you go back here and it's again here. The same distance what I am talking. So this point, this section, no, also this section of the cantilever beam. So this side you have positive bending moment. This side you have negative bending moment. At the same section, one side is positive, the other side is negative. So this section is called as contraflexure. The section which is subjected to contra. Contra means opposite. So section subjected to opposite bending moment is known as contraflexure. Okay, and such a section, okay, is very critical. So you can see anything, you take a wire, if you want to bend, it is not by pulling or even bending in only one direction, it won't cut. You bend it this way, that means both portions, the two portions of the wire are subjected to opposite bending moment. When you take it again like this, maybe a couple of times, immediately it is going to break. So any such section which is subjected to contraflexure law, that is the most critical section where the failure is likely to occur. So we are also supposed to find out at what is this distance. Okay, many times, maybe in another example, I shall take such problem and then find out what is the portion. So you can easily find out. Say this distance divided by 20. This triangle and this triangle, they are similar to each other. If you take this as y divided by 20 is equal to, what is this portion? You know that from here to here is 2 meters. If this is y, then this is 2 minus y. So y by 20 is equal to 2 minus y divided by 120. So if you simplify this, you will be able to get what is y. So it is not impossible for you to find out what is the section where exactly the contraflexure is occurring. Okay, so now I hope you have understood. Please practice such problems. Probably, maybe in our next class, I shall go to what is called as, say, I shall take other type of beams, simply supported beams, or what is called as overhanging beams. I shall straight away pick the problems. Now I am not going to do only a point load, only UDL, only moment like that. Okay, you all are familiar now. I shall mix all the loads in one beam only and try to draw what is called as bending moment and shear force diagram. Okay, all the best. Take care.